we'll start. And in the last class, we defined the notion of angle, and in today's class, we will study the perpendicular, and we can image perpendicular from the angle, because if we give angle cosine theta to for two vectors, then we defined it how to get the angle theta, and if it is same to pi over 2, then it will be perpendicular, and we will say that orthogonal between the two vectors. And so I will record how we get the theta. So the theta, if we given two non-zero vector uv, we defined it the angle theta as the inverse of cosine by using the notation dot products over the norm of u and v. And so by using this equation, we can get the perpendicular. We can get angle, and if the angle is pi over 2, then it means if the angle is pi over 2, then the inverse of cosine of it should be inverse of cosine of 0. So that means u and v are, since u and v are not zero vectors, so the vector u dot product v should be 0. So it makes sense in R to the n space. So we will define the orthogonal or perpendicular like that. For two non-zero vector u and v, I will use just non-bolded. I just use u and v, or non-zero vector u v in R to the n. They are said to be orthogonal if or perpendicular if they are satisfied with the equation u dot product v equals 0. And so in this if you see the definition, if you choose zero vector, then we will agree with that all the zero vector is also to be orthogonal with every vectors in R to the n. In fact, for zero vector for the zero in R to the n is to be orthogonal to all vector in R to the n. So let me give an example. We have two vectors u equal minus 2, 3, 1, 4, and let v be a vector having the coordinates 1, 2, 0, minus 1. Then these two vector is orthogonal in R to the 4. And because we can calculate the dot product of them, and its dot product will be written the products of each vectors and summation for each vectors like this. Then if you calculate it, you can get the results. Minus 2 plus 6 plus 0 minus 4, so it is 0. So we can see u and v are orthogonal. Okay, next we want to talk about the solution space of some linear system finally, and so this solution will be drawn in plane or in space like line or plane. So I will give an representation of the line to as vectors set. So let me give a notion in R to the 2 or R to the 3. If we draw a line in R to the 2, then we might give this line by giving a point p0 and this slope, how slope the line have, and then by also in three-dimensional vector space case, also we might think of plane, and it has inclination like slope, how many slope in this space, and also what points will go through, pass through. And so if we can get a very information of inclination or slope, and if we know the points P, and it will be written the coordinate in R to the 2 or R to the 3. So we already know the information of P0, so we will define the information of slope or inclination, and Actually, I will give the I will give this notation by using orthogonality. So if we might consider that you have a vector and this line will be have orthogonality from the vector u. In this sense also same. If we have a vector u and this plane will be orthogonal to the vector u. And this vector we will say normal vector, and in this situation we say the point normal. And so if I write it, then line or plane case, if it throw a point, the point P0 and having normal vector n, and we will write it is a comma b comma c as a vector. If we translate the vector through having origin to start from origin, then the coordinate will give the vector's information. And the line, so line or plane will be represented by the set of points in R to the 2, respectively R to the 3, with the which is satisfied with the equation and the product P minus P0 equals 0. Because we defined it, each point is orthogonal to u, to the vector u. I used u. I will note n. It is orthogonal with the vector n. So, and we defined the orthogonality by using the equation. The product is 0. So if vector in slope, if we get a any vector in slope, then it will have the orthogonality to the vector normal vector n. And so when you are in high school, I think you learned the line equation or plane equation. And in this case, by using this dot product system, we can denote we can induce the equations. So let me show that. And this is quite simple. Non-zero constants A, B, and C. Then the following equation the form ax plus by plus c, or not c, d equals 0. In plane case, we learned that the equation cz plus d equals 0 will will represent a line in R2D2 is the x-axis and y-axis, or respectively a plane in R2D3 as the axis xyz. So it is induced from the fact of above things, because the all vectors in line, if we denote it p minus p0, then its dot product with the normal vector n will be give the result 0, and so it will give the form. If the homogeneous case, it will be the form ax plus by equals 0, and it is same a comma b dot product x comma y equal 0 when d equals 0. So by using this form, we might get the information of line or plane by using the vectors, especially normal vectors. So another line or plane will be the translation to in the space. So if we get homogeneous line or plane, if I consider the line L, then by translating to throw a point, the point P0, then the line will, we can get the line through the P0 having the normal vector n. So we will focus on homogeneous solution in the space. I said homogeneous, so I will record the homogeneity. So the following equation ax plus by, as I said, and or x plus by plus cz equals 0. This equation is called homogeneous equations. And in this case, as I said, we can denote them the vector n dot product x equals 0, and in this case, first case, n equal a comma b, x equal x comma y. Similarly, the second case is n equal a comma b comma c, and the vector x is x comma y comma z. So by using this, we can denote the line through the origin by using dot products. So next, I will focus on the decompose in a philosophy of mathematicians. Many mathematicians, they like the what is important information in them, and in this sense, we want to get the irreducibility or universality, because if we focus on every object in the object, then it is hard to study all objects. So what is important objects in this sense? So we, in this sense, it is natural to think decompose. So let me give an example. By using orthogonality, we can decompose the vector as another vector's linear combination. For example, let U and A have same initial point Q. Then I will give a process by dropping a perpendicular from let vector having from Q from the tip of U to the line 08. I mean, by drawing it, we have two vectors, U and A, and the tip, the initial point is Q, and the tip of the U will project to A, having perpendicularly. So we will say this vector, we will give a name of this vector. So the vector is called it, we will give the name W1 from Q to the foot of the tip of U. And finally, we give the name W1, and if we give the final vector from W1 to U, especially this vector, and this vector we can denote U minus W1 vector. So the vector will be defined as W2. Then by the construction we can get this decompose of U. Finally we get U equal W1 plus W2, and by the construction, by the way of construction, we can get the orthogonality of W1 and W2. It has orthogonality. That means W1 of W2 equals 0. And we saw that in the space R to the 2 or R to the 3, However, it makes sense in R to the n space, all R to the n space. Let me show that. And in this sense, we might want to know what is W1 vector, and it will be written the scaling of A. So if I bring a scalar K, we can denote W1 vector as KA vector. So let U and non-zero A for non-zero A be vectors in R to the n. Then U can be expressed in exactly one way that means like this, following this process in the form U plus W U equal W1 plus W2, and W1 is having same direction with A by scaling K. Also, W1 and W2 are perpendicular. As a proof, we will denote W1 vector is a vector as by scaling of A. So let me use the notation same. I will use same notation for scalar K. Then our goal is making U's decomposed to W1 plus W2, and we denote W1 is K scalar multiplication to the vector A and plus W2. And we in first process we denote the we dropped to perpendicularly. So we know that the vector W2 is orthogonal with the vector A. So I can write that W2 is to be orthogonal to A. So it holds that U and A. If you calculate U and A, it was the form K equal to A plus W2 dot A, and we have the distribution rule of them, so it can be written K A dot A plus W2 dot A, and we know that it is 0, so and it is same norm of A square, so it can be written K norm over A of square. And so we already have two vectors U and A, so we know we can find the value of K norm of A square. So by using this, we can denote the vector W1 was k scalar multiplication A, and k was by this equation we can get the value of k by using square of norm of A u dot product A, and this direction the vectors A, and finally we defined the vector W2 as vector u minus W1, and so it is u dot product A over A square of norm of A dot A. And we might be able to check the orthogonality W1 dot product by calculating W1 dot product W2. It is just I by checking the another. Okay, I will calculate now. If we calculate it, then it is A square u dot A dot product u minus u dot A over square of norm A, and by if we calculate it, it remains I will write this W1, then W1 dot product u minus W1 and W1 u minus W1 dot W1 is it right? Maybe wait, I will think the calculation. U vector minus W1 W1 and W2. If we calculate W1 as a K dot product A, we can denote it differently. I will rewrite. Sorry. W1 vector was a K dot product A and W, and we can calculate it. It has associative rule, so we will calculate A dot product W2, and W2 was this vector, and so by calculating u dot A over A square A, it is u dot A u dot A, and it is same to the norm of u dot A. I misnoted A dot A because as the distribution rule, then it will be cancelled, so it remains u dot A or A dot U. The dot product has commutativity, so it is 0. So we can see the vector has orthogonality. So this vector, if we follow the process, then this vector has exactly one vectors, and so we might say that we might give the name of the vector W1 and W2. So we used the notion of projection, so we will give the name by using projection. I will use the same notation, and the W1 is called it orthogonal projection. Orthogonal projection of U on A. That means exactly we are seeing the vector W1 as an orthogonal projection of vector U on vector A. And W2 is called it the vector components of U orthogonal on A, orthogonal to A. I think we do not use often this name. We usually will say the orthogonal projection of U on A, and it is W1. The vector W1 is commonly denoted by projects of A of U, and we get the vector Wn as this form. So it will be defined U dot A over A square dot A. As an example, I will give two vectors in R to the 3. One is vector U is 2 minus 1 3, and vector A is 4 minus 1 2. Then in this case, we can calculate projection of A of U is by calculating then dot product A, and norm of A is equal to A dot A. So 4 minus 2 minus 1 2, 4 minus 1 comma 2. The direction is same to A, and if you calculate it, 8 minus 2, 8 plus 1 plus 6, 15 over 4, 16 plus 1 plus 4, 21. And so it has same direction to A, and the W1 vector is written the scaling of K of vector A, and W2 vector will be U minus W1, and U vector was 2 comma minus 1 comma 3, and W1 vector is I will use reduced form. It is 7 5, and 5 over 7, 4 minus 1, 2. And if you calculate it, you will get 14, 20 minus 6 over 7 minus 2 over 7, 3 minus 21 minus 10, 11 minus 11 over 7. This is the vector W2, and I'm sure you can calculate the dot product by W1 and W2. If you calculate it, then you will get the orthogonality by two vectors, W and W2. I will calculate the vector form, then W1 dot W2 is, I will write it K1, K2, then K1, scalar K1, K2, and 4 minus 1, 2, the product 6, 2 minus 11, then K1, K2, 24 minus 2 minus 22, so it will be 0. So it is makes sense, and theorem is correct. And then I will give some geometrical information of them. We saw that by using the projection and orthogonality, we can find the linear transformation of projection or reflection. We give a special case of projection and reflection. However, I will give the generalized form. And we have seen that the projection of if we get a vector a comma b, then if you project it as a standard basis, then it will give a projection map a comma 0 or 0 comma b. However, we can consider another projection. We will use same vector a comma b, and by choosing a line, and we can project to the line the vector a comma b. The line has let the line have the slope theta. So I will denote it. Wait. As an example, I will write first. The question is that find. Firstly, we will find the. I erased. Firstly, we get the projection to the positive way, or positive x-axis. So by using them, we can we rotate the x-axis line to having the theta And we can calculate it. I will divide the process as a two process. So firstly, we calculate standard unit vector E1 0, and E2 in R2D2 space. And it is projects onto the line L. It is line L. That make the angle theta. And then we can calculate it by using linear, by using the linear transformation. I will denote this point is 1, 0 and this point is 0, 1. Then the standard basis will I should note in the below points. I will denote this point is 1, 0 and this point is 0, 1. And we will project to the line L, and then we calculating the vectors to project to L. Then the L, if L is has set the angle theta, then the 1, 0 will project. It is to write the point vector in L, and I will denote A1, B1. And if I give the vector A, it will be this A, and A have the coordinate cosine theta and sine theta. Then we can find the projection of the vector E1 and E2 on the vector A, cosine theta, sine theta. So A E1 is equal to E1 dot A square A, and A was normal vector. A has the norm 1 because cosine theta square plus sine square theta is 1. So it is 1, 0 dot product cosine theta, sine theta. The direction is A. It is cosine 0, sine 0. And by calculating it, we get the vector cosine square theta, cosine cosine theta, sine theta, because it is will give cosine theta, and by scalar multiplying to this vector we can get this. And similarly we can calculate as E2 of projection on A, and E2 dot product A will give sine theta, and so it become cosine theta, sine theta, comma sine square theta, and we can denote it as a transformation by using matrix form, and it will be T1 vector T of E2 vector is cosine square cosine theta sine theta, and cosine theta sine theta sine square. It is the linear transformation to project to the line L. And if I write it more simply by using the rule of sine, addition of the angle, then it can be written this form. And in particularly, we see when the theta is 0, that means when we project to x-axis, then by inputting theta equals 0, it will give the value in the matrix 1 0 0 0, and it is a projection matrix for each vector in R32, because if we give the vector x comma y, then it will project to the x-axis x comma 0. And by using this, we can generalize the reflection linear transformation too. Because reflection can be seen as a result of the projection. I mean, we will see in R32 space, and we have the line L, and if you want to find the point, I will just x comma y. For any point, arbitrary point x comma y, it will go to the point x prime comma y prime. We don't know yet. However, calculating the projection, then I will say it is for the x. The vector x by calculating the vector w1 and w2, then w2 x will be written w1 plus w2 vector this way, and from this minus w2 will give the vector this way. And so the linear transformation reflecting is by calculating double and by editing the vector x, we can get the reflection. I will write reflection transformation as h sub theta. This point is theta. If we enter the vector x, then the vector x will give the vector w2, and by calculating x plus 2w2, we can get the value of the result value. And in this sense, I will write it. Then it is the result of projection, and I will say projection matrix is P of theta, P sub theta, and so it gives the equation P sub theta of x vector minus x vector. That means P sub is it means the minus W2 because it is the P zeta x and this vector is x, so minus x plus P sub zeta x will be minus W2, and it is we say that if we calculate but if we multiplying 2 to the h, then we will get I will let it with this h zeta x minus x is I think it is minus 2. I missed. Because this way is minus 2. Minus W2. And so it will give the minus W2, and then this equation satisfied it 1/2 h zeta x minus x, and by moving x we can denote it is same. We can make same equation by calculating it. 2 p zeta x minus I will calculate 2 and remove x, and it has then P of x is same the vector P matrix multiplication x, so I will rewrite it P sub zeta minus identity matrix, and we calculate already the matrix P sub zeta, and then it is cosine square 1/2 sine 2 zeta 1/2 sine 2 zeta sine square minus identity matrix by matrix multiplying x, and then it cosine square minus 1 is cosine 2 zeta, and so by using this notation 1/2 cosine 2 zeta, so by using this notation we can calculate it multiplying 2. I will write this one first. Minus 1. Am I wrong? Wait. This 2. The multiplying 2 p zeta x minus 2x, and it will this form will calculate will cancelled, and so it is same 2p x zeta minus x, so I missed it, sorry. And then this is right. So 2 cosine square and sine 2 square, 2 cosine square minus 1 and sine 2 square, sine 2 theta and sine 2 theta, 2 sine square minus 1, and sine square is same to 1 minus cosine square, and so we can calculate it as cosine 2 theta. This is cosine 2 theta, sine 2 theta, sine 2 theta, and this form is minus cosine 2 theta because it is same to minus cosine minus 2. This is same to minus 2 cosine square theta plus 1, and so it is minus cosine 2 theta. And it is we want the reflection with linear transformation. And when theta equals 0, that means if we find the reflection to the for the x-axis, then it gives the linear transformation 1, 0, 0, minus 1. And if you give the vector an arbitrary vector x comma y, it will give x comma minus y. So we can see it is really reflect by x-axis. X comma y goes to x comma minus y. So by using orthogonality, we can get the linear transformation of reflection and projection. And I think similarly, if you calculate in 3 dimension by 1, 0, 0, 0, 1, 0, 0, 0, 1, if you calculate it by the linear transformation, you get the linear transformation in R to the 3 space also as the same value, because we defined the projection in R to the n, and it is defined as the dot products. So by calculating dot product, you can get the matrix rotation in R to the 3, R to the 4, R to the n. Next, we go to the maybe elementary mathematics. You would learn what is Pythagoras and Pythagoras rule, and it is quite close to the orthogonality, because Pythagoras rule says that each edges nearby perpendicular angle, it is A and it is B, then its length is square root of A square plus B square. And in the vector space, we can do same notion. It's quite simple, and the proof is also simple. Let me u and v be orthogonal vector. Orthogonal in R to the n. We will generalize in R to the n. Then we get the equality. Then it means it means if you translate it then to the origin, then u vector and v vector and u plus v vector is that then u vectors square the norm of u vectors square plus the norm of v vectors square will be same the norm of the u plus v vector square as Pythagoras rule. So it means same with Pythagoras rule. So if I give the proof, the vector, we used the orthogonality of vector u and v, so I will use it. Since u and v are orthogonal, it should be satisfied that u dot product v equals 0 as a definition of orthogonal, and which follows the calculation u plus w dot product u plus w, and it can be written 2u dot product w of v plus norm of square of v, and we have the value of dot product is 0, so it is same to u square plus w square. So the Pythagoras property, Pythagoras rule or Pythagoras property is satisfied in R to the n space also. It is Euclidean R to the n space. And if we give the angle, then we said, firstly we said that the vector has the direction and the length, and the angle gives the information of direction. Then we can bring all information in the for the vectors, and so I wanted to talk about the distance for for vector and line or vector and plane. It is actually not exact vector. If you have a point in R2D2 space, and if you have line L, then you might consider the distance between two objects is this length, and similarly in R2D3 space, if you have P0 and a plane, then you might say this length is distance. So for the distance, we can calculate the distance by using projection, because by projecting the point P0 to L, then we will get the vector information for this, and usually we will translate from homogeneous form L T0 prime L prime. It is just translated from this, and then the D has not changed. So by calculating the projection of the vector P0 prime projects to the line L prime, then we get W1 and W2. This is W2. And then by calculating W2's norm, then we can get the distance D. In this sense, let me give the, I will write the space also. In R2D2, respectively R2D3 space, the distance D between the points P0, it is will be return x, 0, and in the space R2D3 I will write x, 0, y, 0, z, 0. And the line, we said the line or plane can be written as the equation. More precisely, the solution set of this equation will be drawn as a line, and respectively the plane will be written the set of solution of this equation, and then the distance will be norm of W2, and that means it has the dot products as a numeral by0 plus c, and as a translation by dividing the norm of normal vector, not normal vector, norm of the vector A, the line L to line L, and respectively in point and plane case, ax0, by0 plus z0 plus d, a square, b square, c square will be this. And just by calculating W2, you can get the solution then. Okay, then I will enter the next chapter, next section. We are focusing the geometric concept, and I will introduce the set of solutions of linear system, and I said it will be written as a line or plane or hyperplane in R to the n. And then if you use parameter, then you can write them more exactly, more precisely. So let me give one example. If let's consider the situation. There is a line L through x0, and let the non-zero vector v let a non-zero vector v be parallel to the line L. Then this means in the space there is a line L, and there is a vector parallel to L. And then if you bring an arbitrary point x0, and if you choose another point x, then you will get the vector in the space in the line L as the vector s minus x0. Oh, I will rewrite it. This point is x and this point is x0. It is fixed point of x0. If you bring for any vectors in L, then it will be same the scaling of v vector. So the x minus x0 will be written t scalar multiplication to v, and equivalently it is same to x0 plus tv. So by using this notation, if this L was the set of the solution of linear system, then you can rewrite the elements vectors as this form. So that means it in plane case also we can use same notion. If you choose x0, and if you have two vectors parallel to this plane, inclination to this plane, v1, v2, and it has different direction, then in plane case will give similar solution. So I will write let p0 be P0. Let cosine is p. Here. Oh, I think I missed right in my notes. The plane in R to the n. And that contains the point x0 and we have two vectors, two distinct direction vectors, v1, v2. Then we will use this notation, and for x in the plane P, the x will be written x0 plus t1 v1 t2 v2. Because it has parallels, so by moving the initial point to x0, then by adding the vectors v1 or v2, it will move in this plane. And conversely, if you choose some point in this plane P, then it will be written as a linear combination of v1, v2 by making I forgot the name of this. By making rectangular, I think it is not rectangular, parallelogram. So I will define that line or plane. So x0 by basing on the previous theorem. Let x0 and non-zero vector v, or in the case for plane case respectively, we will give non-zero vector vn v1 v2 in R to the n. Then the line through plane also through x0 is defined as the form, the two form. X equal x0 plus tv respectively. The plane case is x0 plus t1 v1 t2 v2 for all t1 t2. And for an example, let me give one example. We'll find the vectors in the line, and I will give x0 is 1, minus 2, and the non-zero vector v is minus 2, 3. Then it will give the line, and the line will be written by x is this form, 1 minus 2 plus t minus 2, 3, and this t is called the parameter. By using parameter t, we can write this, and by calculating it, we can get the vectors x space by 2 plus 3t, like this. And also by giving, in plane case also we have same things, and we say the plane or lines can be written as an equation, and finally we will see, I forgot to geometry or linear system. So the linear system will be given as an equation, and the line or plane, or more general plane, which is called the hyperplane, will be written equation. And so if I give an equation x minus y plus 2z equal 5. For this equation, we can get the solution set also by using this form. Because by removing the y and 2z to the right side, then we get x equal y minus 2z plus 5. And actually in the chapter 1 we use the same way by inputting t1 and t2 as a parameter, as the parameters. t1 minus 2 t2 plus 5, and this form can be written if we give so if we find the solution x comma y comma z, then x is t1 minus 2t2 plus 5, and y was t1, and z was t2. And if we denote this form, if we denote it like this form, then by having parameters to vectors, we can denote it. Firstly, 5, there's no parameter term is 5 and 0, 0. And having the coefficient of the parameters t1 is 1, 1, 0. So 1, 1, 0, and the coefficient of t2 is the vector minus 2 t2 product minus 2, 0, 1. And so the solution set will be written these three vectors having two parameters t1, t2. And also by giving the restriction of the domain of the parameters, we give the all values to T1, T2. In this case, T and T1, T2 is in any scalar in R. However, if you give some for some restriction to to T parameter T, then you can get line segment. So I will define the line segment by using the parameter T having restricted domain. Let x0 and x1 be vectors in R to the n. Then the line segment from x0 to x1 is defined by the equation having limited domain of parameters. The equation is that having same equation by using parameter, it will start to x0 to x1, then by using this form, you can calculate when t equals 0, it will be go to x0, and when t is equal to 1, then it will be x1, and equivalently it is same 1 minus tx0 plus tx1, and for 0 to 1 t. It is quite convenient notation, and so we often use this notation. And finally, I will remark, I said the linear system has linear equations, and the solution set will be written by this form by using parameters. And so if I illustrated so far, for an equation, for a linear equation a1 x1 a2 x2 an xn equal b, it is an equation, and it can be written as the dot product a dot x equal b, where a is x a and x are vectors having the vectors a1 to an, x1 to xn, and also the homogeneous form case in homogeneous equation case, it will be written a dot product x equal 0 because the homogeneous form was b equals 0. And by using then the linear system can be written the intersection of the solution sets, the set of solutions, and so in this chapter, finally I will mention the binary theorem. Of course, indeed it is not binary section in this chapter. We remain one more chapter, however, I will do this today. Let A be an n by n matrix, and we will call it augmented matrix, and the solution set of homogeneous linear system A x equals 0 consists of all vectors in R to the n that are orthogonal to every row vector in A of A. Because it will give the equation A11, A12, A1 m by n, A21, An1, Amn, x1, x2, xn, it will be 0, and for each term will give one equation, and its equation means A dot product x equals 0, and that means the vector A and x are to be orthogonal. So for all row vectors, the solution vectors will be orthogonal to all row vectors. If I apply the first equation, then I will write it is A1. Convenience. A1 x equals 0, A2 equals 0, so An m x equals 0, so that means x is orthogonal to all row vectors. So the solution set of linear system can be written by using dot products, and it gives the orthogonality when the linear system was homogeneous. I will talk so far here. I will talk until here.